paper gyrification or brain folds.
A neuroscientist started to look at the brain
as like the
more as an
network
interconnected
are very
incredibly negative
area.
They're parasites.
Cool. Hi, everybody. This is so exciting. I don't normally get nervous talking, but it's fun to feel nervous. It's like exhilarating, kind of. I feel like I'm at like qualifying exams or something. So that's so hopefully it goes well. Hopefully it's fine. So hi, everyone. Welcome to my talk today about finding intuition in the abstract photosensitized catalysis. We're going to be talking about a paper that was published in 2017 from the lab of David McMillan. You may know him because he just won the Nobel Prize for chemistry. This is based out of Princeton. And we're specifically going to be focusing on this reaction here, which we'll see later. We're going to diagram this. And this was pretty exciting stuff. When I was in grad school seeing this paper, I was like super jazzed. So my personal draw to this topic really stems from my time in chemistry in the 10th grade in 2009. I really fell in love with the topic, but I more so fell in love with the idea of coming up with these models to help me interact with and understand things that go beyond my sort of daily experiences, right? So specific topics that were super interesting to me and continue to be, like what is an electron? How does radiation interact with matter and vice versa? What is thermodynamics? Specifically, what is entropy and why does it matter? And then like what is a chemical bond and what is the nature of bonding for atoms? Today, specifically, and in this paper, we're going to be talking about how does radiation interact with matter. So the goal for this talk, right, is to begin this process of all of us developing some type of intuition about how does radiation interact with matter. Okay, so to do that, we kind of got to get a little bit of backstory. So here I've shown a chromophore, which is fancy speak for some molecule that can absorb light, right? Here I'm showing we have incident radiation, and when you hear radiation, you should also think, okay, there's some energy associated with that. So what can happen, right, if you expose molecules to radiation? Well, one example that I like is if you expose carbon dioxide to infrared radiation, you can induce a vibrational excitation, literally changing how things are moving. This has major consequences for us, right? This is a reason why carbon dioxide is a contributor to greenhouse effects. Okay? Another thing, cool thing, is that some molecules, right, will fluoresce if you expose them to certain types of radiation. So here we have tonic water, which has a molecule in it called quinine, and if you put UV light, you can't see it in the light, but it's fluorescing, right? This isn't, the blue you see is not the UV light, right? There's a molecule in here that's absorbing that radiation and then emitting photons in the blue region. So that's kind of neat. And so this paper specifically is focused on how does radiation interact with electrons in molecules. So if you're taking my chemistry class, these diagrams should look strikingly familiar. We have a version of a propagating radiation wave, which is a perpendicular magnetic and electric field moving through space, right? And on the left here, I have an energy diagram for just, we'll say, like a simple atomic structure, right? There's electrons and atoms. This is explaining sort of like what can their energies be? So what might happen if the electron, on this example, on the first level, what would happen if it gains 5 joules of energy? Any ideas? What might happen? We'll transition energetically to the second level, right? The first level has 1 joule of energy, the second level has 6, right? Two things that are really important from this very simple diagram. One, the animation I just showed the electron physically moving somewhere. When electrons absorb energy, they do not necessarily physically move. This diagram is just used to show that, so it's not necessarily a physical movement. It's just it gains some energy. The second thing that might be funky about this, you may be thinking, well, okay, I see, level 1, level 2, 3, 4. We have some energies associated with those. Is there something in between 1 and 6 joules? Could it gain like 2 joules of energy and do something? The answer is no. It is a strange artifact of atomic structures that the energy levels available to electrons occur at discrete quantized levels, right? So it does not exist on a continuum. If the electron were on the first level, it couldn't gain 2 joules of energy. It just won't happen. The radiation will just sort of pass it by. You can think of it that way. Alternatively, instead of absorption, we could have emission, right? So in this example, the electron's on the 4th level, It has 10 joules of energy. What might happen if it transitions to the first level? How's it going to do that, right? I saw some hands, right? Yes, we have our photon emitters here. So it will emit a photon of energy equal to 9 joules. The photons emitted, the energy of them are exactly equal to the difference in energy between the levels that the electrons transition between. And so fundamentally, everything that's happening in this paper is this. A very simple model just explained a whole bunch of chemistry, right? That's essentially what it kind of boils down to. The other thing we need to talk about is this idea of orbitals. Orbitals you can think of as like a home where electrons are most likely to be found in. So why does that matter? Well, if you have two molecules, here A and B, I'm showing two electrons with another model, arrows, right? If they get close to each other, and in this example, the energy of the electrons in these orbitals are very similar, right? We can mix them together and form new orbitals. We call those molecular orbitals. What's important about that is from the individual molecules can then start populating these new homes and form a bond, right? So maybe we just formed a carbon-hydrogen bond, right? The important thing is that the energy of those atomic orbitals need to be similar. What also happens is that if you have two molecules and the energy of the electrons in those orbitals are too dissimilar, nothing may happen, right? Well, I'm standing here in air. I'm not forming all these crazy spontaneous bonds with the oxygen and the nitrogen in the air. That may have something to do with, right, where the electrons are at in what orbitals. So the implication of this is that if researchers can either, one, change the energy of the electrons, i.e. like what orbital they're in, or actually change the level of energy of these orbitals, you can affect how things bond. You can induce new bonding, you can kill old bonding, you can do all sorts of interesting stuff. So also, before we get into the paper, I want to give credit to like basically the last 150 years of chemistry and synthesis, right? So transition metal catalysis is something that has essentially given us almost everything that we have here today, right? If you've ever used plastic cling wrap, right? That's a polymerization reaction that happens using a transition metal catalyst. One of my favorite ones is the Buchwald-Hartwig coupling, where you take an aryl halide. For those of you in organic chemistry, right? You have some halide bound to a benzene ring and a secondary amine. You can couple those together to make an arylamine. I've also showed here this thing called a transition state, which is fancy speak for the thing in between the reactants and the products, right? What's important about this is you see that things are connected to that transition metal. It brings them in close proximity so that they can form a bond and go off to live happily ever after somewhere, right? And you can also see that there is maybe a charge on that transition metal, so there's movement of electrons, okay? Why is this important? What did we get from this specific reaction? Researchers have synthesized a cyclozosine amine derivative for heroin addiction treatment, and like 1,2-aziridynamidosine, key substrate for anti-tumor therapies, right? So like we're getting useful things from these reactions. Plastic cling wrap, maybe the most useful thing that we have. What's important about this, and I've shown a hand-drawn model to show you that drawing things and having these ideas in your own head is very important. What's happening really is reduction and oxidation chemistry. And so the paradigm, though, is that the movement of these electrons to all these things, it's all happening on the same level of the house, right? Maybe the electron goes through this door, maybe it goes down that hallway, right? It forms the products. But it's all on the same level of the house. They all have the same energy. We'll call that ground state, right? Not excited. So what did these researchers think they could do? Well, if they used radiation, maybe they could let the electron onto a different level of the house, right? So on the bottom, we're showing sort of the old style paradigm where the electron moves from like reactants to transition state to products, right? But if we expose it to radiation here shown in yellow, right, maybe we could induce that electron onto a new level, unlock new transition states, new products, maybe make something that we weren't able to make before. The important thing too is that if there's no energy, there's no access to the second floor, right? It's not just going to spontaneously do that. So let's go back to this reaction and think about this. So we have our reactants and our products, right? We have benzoic acid and bromo-4-methylbenzoate here. There's a whole bunch of gobbledygook that mixes it all together. We'll talk about the gobbledygook in a moment, right? And then we get this product of interest. And you may be thinking, oh, is this product like super important? I don't think it is, actually. It's just a fun model system that they came up with that was like, quote, convenient to study, right? So this reaction here may not have any importance, but this new paradigm of reactivity is important. Okay, so essentially what's going on? We have our chromophore, which is something that can absorb radiation, right? This is an iridium-based dipyridyl chromophore. That's what shows up in this reaction diagram as photocatalyst. It catalyzes something using photons or photo energy, whatever radiation. It absorbs that radiation and it can transmit that as useful energy. We also have this transition metal catalyst, sort of like the old style, right? It's a nickel-based catalyst. What's important about that is that it can accept that energy, right? It can bring the reactants close together, bring them in proximity so they can form a bond, go off somewhere to live happily ever after. It can also allow electrons to sort of pass through it, right? It kind of shuttle these things. It can get oxidized, or it could reduce something else. It can take and give electrons, excuse me. So what happens in the ground state, it absorbs that energy, right? And then it becomes this excited state catalyst. And this is like the important thing in this paper that they're hoping is what's going on. They hypothesize in the paper it is this excited catalyst, right, that is the reason why we get the product we get. You can see here there's a simple electron diagram where we promote one of those electrons in this orbital to a higher orbital, right? So maybe now we've unlocked some new reactivity or something. So without the radiation, they're saying essentially that these types of products would not be accessible. Okay, so the previous slide showed sort of your standard chemistry reaction, you know, reactants and stuff, products. That image sort of belies the complexity and the dynamics of this type of situation, right? This image here tries to sort of capture that a little better. So we have on the left our photocatalytic cycle with our iridium catalyst, right? That's what's absorbing the radiation. We can have the unexcited iridium here. It absorbs radiation and it can become excited. There's interplay there where there's populations of both, right? This excited photocatalyst can then energy transfer to this nickel catalytic cycle here. So what's going on is we have one of the substrates, one of the reactants, right, oxidatively associates with the nickel. Then we have the second substrate also interacting or associating with the nickel. It is this ground state nickel complex that they're hypothesizing absorbs some energy, right, is in an excited state now. One of those electrons is now higher in energy. That's where we're able to achieve our product via reductive elimination, right? It leaves, goes off somewhere, it's now been made. So what is important about the paper? What did they emphasize? So I think the main point of this 2017 paper was them trying to start to elicit some proof about this occurring via energy transfer and not some other reason, right? You're trying to say this is what's going on. Because if that's what's going on, then they're going to be able to publish in a very high impact paper, or journal rather, right? This was published in Nature, so at least the editors believed probably, right, their claim is true. And then, you know, what can you use this process for? So these 4 other papers around are published in the same lab in future years, right? So they were able to use this method to bioconjugate proteins. They were able to achieve reactivities that are historically quite difficult, like coupling 2 carbons, 2 sp3 hybridized carbons, right? They're very sterically hindered. It's hard to get them together to make a bond. They were able to make some bicyclopentane, right, which can be used in sort of like cancer therapies, I guess. Those are also difficult, strange molecules. And then in 2020, they published a study of how this process occurs. And by studying this model system, they're able to apply that knowledge to other things, right? More complicated things like Dexter energy transfer between immune cells, yes, in the body, right? Which physiologically, that's a very complex system to study. There's so much stuff going on, right? But understanding this energy transfer can help them understand other types of energy transfers. So what was one of the experiments that they did to show, right, maybe this is occurring via energy transfer? So they synthesized this catalyst, this nickel-based substrate on the left. They said that this was thermodynamically robust and stable. What does that mean? It means someone told a grad student to set it on the counter for a week and see what happened. So they set it on the counter, they left it alone, they came back, and they're like, ah, it's exactly as I left it, right? Meaning it's probably not doing anything. It's just going to sit there, right? These chairs will probably just sit here. Same idea, right? It's just not doing anything. So what they did then was they exposed it to blue light, probably around 415 nanometer wavelength of light, in the presence of a chromophore, and then they were able to see this product, right? So the substrates here are these 2 chemicals, right? They reductively eliminated to form this product. Again, you may be asking, oh, is that a cool product? What does it do? I don't think it does anything, right? Again, this was just a model system that they used to sort of do an experiment. So what they saw, the result of this experiment was when chromophore was present, they were able to observe product via fluorine NMR, for those of you in organic right now doing spectroscopy, at about 30 minutes. So in 30 minutes, they saw product. When chromophore was not there, when they did not have the iridium photocatalyst there, product wasn't observed until about 60 hours. So however many days that is, several days. So based on that, what might you make of this result? What might this imply? Anybody? Any takers? Yes?
I mean, the blue line LED is correlated with the product being observed fast.
Yeah, so I think one of the main ideas from this experiment is that, well, we probably need the photocatalyst there for this to be a useful reaction. Even if it's still possible without the photocatalyst, it's precluded from being useful because it takes 60 hours, right? Do you want to wait 60 hours for your Grubhub? No, that doesn't even make sense, right? You want it now. Same idea, they want these reactions to happen quickly. If you scale this up, you want to be able to make the things fast. Time is money, I guess. Okay? The other thing that they did, right, we're seeing this reaction again. We have our reactants and products. I'm going to show you this sort of process again where we absorb radiation. There's that transfer of energy. What a strange thing that is, right? What's going on there? You spent a whole year talking about that, right? And then you excite the nickel catalyst, you get products. So what they did was they changed the ligands on the photocatalyst. So right now, we have, around the iridium, we have dipyridylamine ligands, right? They changed what those ligands were. I showed an example here where now we've added fluorines. We have a picolinato group here, right? What that does is that it changed the amount of energy that is transferred, okay? And so they saw a correlation with the yield of how much product you get based on the amount of energy that's transferred. There's a positive correlation, meaning the more energy that's transferred, they're associating that with a higher yield of product. So what might that mean? What conclusions might you draw from that result? Yes?
So not only the reaction happens faster, but you also get more of what you want.
Yeah, right, exactly. So I think the idea here was that they were saying, well, if we can have more of these nickel compounds in solution excited at a given time, right, we can kind of get more product. Or if we're not able to give it enough energy, maybe it can't do what it's supposed to do or whatever it's doing as well as if it had more energy, right? If you have 0 energy, can you go run a mile? No. You have a lot of energy, you drink a Celsius or a Bang or something, maybe go run 15 miles, right? Similar idea, kind of similar idea. So conclusions, right? Did the researchers find a way to make new molecules? They sure did, right? It was published in Nature, so someone believes they did something important. Is it an improvement on traditional techniques? Yes, in the sense that now we're able to make molecules we were not previously able to make. We're able to get higher yields, right? They were able to sort of optimize this process to get the products they wanted in as high a yield as they're able to. And we're able to get greater selectivity, right? We're able to have these molecules link up in a very specific way, not have like a whole melange of things. Where did this go next? So again, this was published in 2017, so I think at the time there was almost like a windfall of like, ooh, let's be the first to figure this out, right? A lot of groups, I think, were looking at this like, oh wow, this is a beautiful case study. Let's see if we can figure out why this is happening. So they wanted to do in situ detection, right, using structure specificity. What that means, that's kind of fancy speak for like they really kind of want to take a video of this process as it's happening. You can sort of see like, oh, this thing got excited here, this one, got excited here. The difference for that would be like if you collected a static infrared spectrum, you would sort of just have a photo. You would just be like, okay, at time 30 seconds, this is what was happening. They can do in situ detection. You can see in real time what's going on and try to deal with those dynamics. So like in what order did the molecules become excited? How long do they stay excited? And which things got excited? Did anything get excited? So they did that. They published that study in 2020 using a pump probe spectroscopic technique, which is one of my favorite things. What's essentially happening there is you have 2 types of radiation. One type of radiation goes in, it excites everything. The other type of radiation goes in and it measures stuff. So you're able to like do this in real time kind of. So at the time, I had a very similar idea when I was in graduate school. I wanted to do a pump probe spectroscopic setup. So here is data that I collected in probably 2018. I'm showing you this catalytic cycle again, and I've color-coded things. So on the bottom is an infrared spectrum, right? It's showing sort of these vibrational modes, like literally things are vibrating, of these different compounds. So you'll see the yellow trace corresponds to these dipyridylamiine groups there, how they're vibrating. You'll see that the green here corresponds to the product, and the blue and the red correspond to the substrates. Now what's exciting about this is that at one time you're able to sort of resolve all of these different things. So if I mix them all together, I can collect information about the photocatalyst at 1600 wave numbers. I can see the product down here at like 1750 wave numbers. Yes, there's a little bit of a mix up here. This would probably look on an actual infrared spectrum as just one big peak, right? But this was really exciting because we were like, ooh, we can like excite this system, and then we can like watch what's going on with all the things at once, right? Maybe these peaks start to shift around. That would tell us one thing. Maybe the intensity of the peaks also starts to change. They get bigger, they get smaller. That would also tell us some really useful information. So I made my pump probe spectroscopy. I used a neodymium yttrium aluminum garnet laser, super loud, right? And it was shooting this really fabulous purple light everywhere. You could catch a piece of paper on fire if you put it in front of the beam. We had to wear these crazy goggles. We had these big curtains everywhere. And so then we also had a glow bar there. It looks pretty benign. It was about 1300 degrees Celsius. Not benign, right? And then we had a calcium fluoride cell. Seems simple, super expensive, so easy to break. It's like they want to break, right? Anyway, so we were able to pump the sample with the laser light. We're able to excite the iridium catalyst. And then we're able to study it using the infrared radiation that comes off of our glow bar. It goes into this diffractometer. And then we use a mercury cadmium telluride detector, right, to make sense of whatever that information is coming in. So here I have a real-time image. You can actually see the iridium catalyst fluorescing here. We had the cell cut, we had like a film in the inside so that one side would have the chromophore, one side did not. So we had like a control and the experiment happening at once. We're collecting information about both. And so that was pretty cool. This was on the website for my research lab at the time. I'm not credited for the photo, but I took this photo. And so, right, that's sort of the conclusion, right? That's not the full story. Hopefully you have questions. But the point is that now you maybe have the beginning of a model for understanding maybe how radiation interacts with matter. And so thanks to the DATA's team, thanks to my 10th grade chemistry teacher, Miss Monroe. I hope she's doing really well. My 12th grade chemistry teacher, Mr. Koshak, and a whole host of professors who inspired me along the way. Also thanks to my fabulous, sweet, precious angel dog. These QR codes take you to a Google folder that has all the papers I used to do this and the presentation. So if you're interested in looking at these things, you can. And now I guess I'll open it up for questions.